Hello, welcome back. This is section 2.2. We're going to finish this section up, and this is where we're going to start in our notes. It's right where we left off after video number 3. So what I've done here in your notes is copied the property of limits at infinity, and they look just like the limits at a specific value. So we can add limits, we can multiply them, we can multiply a constant, we can divide as long as the limit in the denominator does not equal 0. So let me show you an example of applying that. Let's take a look at the limit as x approaches infinity of 5x plus sine x all divided by x. So what we can do is use some of these properties. The first thing I'm going to do is actually split this into two parts and divide this first term by x and divide this second term by x. So I'm going to have the limit as x approaches infinity of 5x divided by x plus sine x divided by x. And now using the property of limits, I can take the limit of each part. So 5x divided by x is just going to be 5, and the limit at infinity is going to be 5. So this is going to equal 5 plus the limit as x approaches infinity of sine x over x. And if you remember from our last video, the limit at infinity of sine x over x is actually equal to 0. So this is equal to 5 plus 0, which is equal to 5. So using property of limits, you can manipulate the limit, and it can help you solve that. So let me show you graphically what that looks like. So here's the sine x divided by x, and as you can see, at positive infinity, that limit is approaching 0. Okay, and then I'm going to go back, and the whole problem was 5x plus sine x all over x, and we can see that that limit is approaching 1, 2, 3, 4, 5. So our answer is correct. We can verify that graphically. Okay, so that's how you can use property of limits. So the next topic we're going to talk about are vertical asymptotes. So let's consider this function right here. Let's sketch the function below, and we're going to consider the limit as h approaches 2 from the left to the right. So going back, I've preloaded all the graphs because we have quite a few, and I thought that would be really painful to watch me type all that in. So continue. We looked at that one already. Here, instead of h, I used x. But the function is 1 over h minus 2, and in my calculator it's 1 over x minus 2. And I can tell that there's a vertical asymptote right here at x equals 2, and that's because when x equals 2, my denominator becomes 0, and then that's undefined. So in our notes, let's go ahead and sketch that. I might move over here because I got a little bit more room. So at positive 2, all right, okay, I already forgot. I think it goes like this. And then like this. Okay, so that's what that graph looked like. So let's consider the limit as h approaches 2 from the left. So if I'm coming from that left-hand side, my limit is going to be negative infinity. So the notation is going to look like this. The limit as we'll use the correct notation because they used h's here. As h approaches 2 from the negative side of 1 over h minus 2 is equal to negative infinity. And the limit as h approaches 2 from the positive side of 1 over h minus 2 is equal to positive infinity. So I'm approaching from the right-hand side, that's going up to infinity. So this is the important part here. Vertical asymptotes occur at values that cause the denominator to equal 0. So let's take a look at this problem. Find the vertical asymptotes of g of x equals 1 over x squared. Where would be the vertical asymptote? X cannot equal 0. So we know that there's a vertical asymptote here at 0. So I'll just kind of draw over it. I also know x squared is always going to be positive. So I have a feeling that my graph is going to look like this, and then like that. So let's check with our calculator, see what we get here. And sure enough, as x approaches 0 from the left-hand side, it goes to infinity. And as x approaches 0 from the right-hand side, it also goes to positive infinity. So going back to our notes, the limit as x approaches 0 from the positive side of g of x, I'm just going to do shorthand, is equal to infinity. And the limit as x approaches 0 from the negative side of g of x is equal to infinity. And I just want to remind you, you have to put the function in there. You can't have a what they call a bald limit where it's just a limit but no function. So make sure to include your function. Now you might think that the limit is actually equal to infinity, but remember, infinity is a number. And infinity is just an idea. It's not a numeric value. So therefore, anytime a limit equals infinity, the limit does not exist. Okay, so if our limit equals infinity, it does not exist. Okay, so let's take a look at these scenarios, these three first scenarios, and we want to figure out where the vertical asymptotes are. So let's factor, and you want to factor the numerator and the denominator. So I think this is going to be x plus 4, x minus 2. Yep, that looks right. Nope. No. Yep, that's right. Okay, and then my denominator, I'm going to have an x plus 2 and an x minus 2. Okay, so these two factors right here cancel. So at x equals 2, if I put a 2 in here, it's still undefined, but there will just simply be a hole in the graph. But right here in the denominator, if x equals negative 2, there's going to be a vertical asymptote. Okay? Let's take a look at this scenario, cotangent of x. If you don't have your calculator, let's think of cotangent x as cosine x over sine x. And what we need to think of is, when does sine x equal 0? So there'll be a vertical asymptote at x equals, so you need to imagine your unit circle, at 0, pi, 2 pi, and on and on. Okay? And then finally, let's look at f of x. You can't factor x squared plus 1. We're just stuck with that. Can't make that any simpler. But x squared plus 1 is equal to x plus 1, x minus 1. None of these factors cancel. So therefore, there's going to be a vertical asymptote at x equals negative 1, because that would make that equal to 0, and x equals positive 1. So what we can do to apply this is we can use our understanding of vertical asymptotes to help us figure out what the limits are at and if there are any infinite limits. So let's take a look at this right here. We know that there's going to be a vertical asymptote at x equals 2. Okay, so I'm going to draw that. Okay, now I need to figure out, as I'm going from the right-hand side, is it going to positive infinity or is my graph going to negative infinity? So the right-hand side would be like a 2.01, for example. So if I do 3 over 2.01 minus 2, that's going to be a positive number divided by a positive number, because that would be positive. So as this number gets to be like 0.01, 0.001, 0.00001 to infinity, this number is going to become a lot bigger, and it's going to be positive because I'm going to have a positive divided by a positive. So without using a calculator, I know that that's where the graph is going to go, the direction of the graph from the right-hand side. And conversely, from the left side, if I go to the left of 2, that would be like 1.99. Let's try that. So that would be 3 over 1.99 minus 2. And this denominator is going to be negative. So now I'm going to have a negative 0.001. And so therefore this is going to be going to negative infinity because all the values getting closer to 2 are going to be negative from the left-hand side. So I know that it goes like this. So the limit as x approaches 2 from the negative side is going to equal negative infinity. And as x approaches 2 from the positive side, that's going to go to positive infinity. And both of these limits do not exist because the limit that equals infinity, positive or negative, does not exist. But this is the direction that the limit is going. Okay, let's take a look and verify and see if we're right with our calculator. Oh, whoops, wrong calculator, sorry. Okay. So let's see. Oh, these are the other 3 problems that we worked. So these graphs, we didn't take time to look at them, but here's the first graph. So if you graph that first graph, you'll see there's an asymptote at -2. For cotangent, you'll see there's a graph at 0, pi, 2 pi, etc. And then the next problem was this one where we had an asymptote at -1 and 1. So those were the previous problems. I jumped ahead. And here we go. We have a vertical asymptote at 2. From the right-hand side, we're going to positive infinity, and from the left-hand side, we're going to negative infinity. So without even using a calculator, we were able to figure that out. So good job to us. We did a nice job. Okay, let's apply the same strategy to a couple other problems. So a limit in which f of x increases or decreases without bound, so that means goes to infinity, as x approaches some number is called an infinite limit. So we've just explored those. Although the notation states that the limit is equal to positive or negative infinity, the limit does not exist. We've already discussed that. So let's find the limit from both the right-hand and left-hand side of this. So on this first example, we know that at x equals 1, this is undefined. So therefore, we know we have a vertical asymptote at +1. So let's go ahead and draw that on here. Okay, and let's consider what this would look like on the right-hand side. So this would be like a -1 divided by the right-hand side of 1 would be like a 1.01. I'm just getting kind of close to 1. So this would be a positive number. This would be a positive 0.01. And then in my numerator, I would have a -1. So I know this is going to be a negative value. So -1 divided by 0.01. And so therefore, and I think that's 100. So this is actually on this side going to look like this. Okay. Now on my left-hand side, excuse me. Well, wait, let's finish that up. So the limit as x approaches 1 from the positive side of -1 over x minus 1 is equal to negative infinity. Now let's take a look at the negative side. So that's going to be like 0.99, I think would be a good value to approximate. So if we do that, I might do that up here or over here. It's going to be in the way. -1 divided by 0.99 minus 1, that would equal -1 divided by -0.01, which I think would be like positive 100. So this is going to actually positive infinity. So that's going to look like that. Okay. So the limit as x approaches 1 from the negative side is actually equal to positive infinity. So let's see if we're right with our graph, if we can look at our graph. And we were right. So from the left-hand side, we're going to positive infinity. From the right-hand side, we're going to negative infinity. Okay, I want you to try this one. I'm going to pause it, and you try it and see what you get. So go ahead and pause it, and you try this one by yourself. Okay, I hope you took advantage of trying this on your own. So at -2, you should have identified that there's an asymptote. Okay, and if you consider something to the right hand of -2, that would be like a negative 1.99. and that'd be a negative 1.99 plus 2. And if you think about it, this value is going to be a negative value. This is going to be a positive value. So from the right-hand side, this is going to go to negative infinity. Okay? And then from the left-hand side, let's do negative 2.01. So if we have negative 2.01 minus 3 divided by negative 2.01 plus 2, this value is going to be negative, and this value would also be negative. So a negative divided by a negative is a positive, so therefore that's going to go to positive infinity. And if we check this with our graph, there you go, we were right on that one. Okay, one last thing, one last strategy. This is the dividing strategy. And it's very straightforward. Once you figure it out, you'll really like these problems. So this is kind of what I say is, who is driving the bus? Or who is in charge? So that's really what I call the strategy. And who is driving the bus is the term with the highest degree. Okay, so let's take a look at this rational function right here. And the terms that are driving the bus, or the greatest terms, are going to be this divided by this. And when we have terms of the same degree, so we have a fourth degree and a fourth degree, it's as if those two divide to 1, and the only thing that matters are the coefficients. At infinity, these numbers basically become insignificant. So a 3x to the fourth divided by 3x to the fourth is going to equal 1. Let me just show you one more. Let's say we have x approaches plus or minus infinity of, let's do 4x squared minus 2 divided by 3x squared plus 1. These two terms are driving the bus. They're in charge. But x squared divided by x squared really becomes a 1. So the limit is going to equal 4/3. These are growing at the same pace. A negative 2 and a 1 at infinity are insignificant. Okay, in this scenario, let's see what's driving the bus. So we have a 2x to the 5th and a 3x squared. So a 2x to the 5th over 3x squared. Now, do you see that the numerator is growing much faster than the denominator because of the degree? So at positive infinity, that's going to be, so the limit, we'll divide these into 2. As x approaches infinity, okay, I'm being kind of lazy. Look, I'm going to do this. Of g of x is going to equal positive infinity because the numerator is growing faster. Now the limit as x approaches negative infinity, if I have a really big negative number on top, that's going to be a negative divided by a positive is going to be a negative number. So that's going to equal negative infinity. So this limit actually does not exist. Okay, let's take a look at this problem right here. So which term is driving the bus? This term and this term. These are insignificant at infinity. And an x squared divided by an x squared divides to 1. So my limit is equal to 2/5. Okay? And then finally, we're going to use this strategy of property of limits like we did earlier, and we're going to divide each term. So we're going to take the limit as x approaches plus or minus infinity. X divided by x is 1 plus e to the negative x over x. Do you see how I divided both terms by x? So the limit of 1 is just going to be 1. So this is going to equal 1 plus the limit as x approaches plus or minus infinity of, I'm going to actually move this to the denominator and make that exponent positive. Remember, if you have a negative exponent, you can flip it. That's not the correct mathematical term, but we're going to go with it. E to the x times x. Okay, now at infinity, this is growing much faster. The numerator doesn't even grow at all. So at positive infinity, this is going to infinity. So that's going to be 1 plus 1 divided by infinity is equal to 0. Okay, so the limit as x approaches positive infinity of 1 over, oh, I'm sorry, let me back up. Sorry about that. I forgot my 1. So I have 1 plus, I'm going to leave this plus minus just to save some time. 1 over e to the x, I'm writing the same thing, sorry. This is equal to 0 because your denominator is growing so much faster than a 1, which isn't growing at all. So when your denominator outpaces your numerator, this goes to 0. So that equals 1 plus 0, which equals 1. Okay, I made that more complicated than it is. This limit is 1. This limit, when I move this to the denominator, becomes obvious that the denominator is growing faster than the numerator, and therefore this limit is equal to 0. Okay, that's it for section 2.2. I'll be posting some practice problems for you to work to check your understanding. Okay, thank you. Hope you guys have a great day.